So my name is Roger Kvam. So I've been with Sigma2 and the National Competence Center for HPC in Norway for just over 2 years. Prior to that, I was working with HPC and IT management between oil and gas industry. And before that, I was working for many years in semiconductor engineering with architecture and deployment of regional design and HPC centers in US, Europe, and Asia. I'm here to speak today about Sigma2 and the National Infrastructure for Research in Norway, our policy for industrial use. And I give some examples of traditional use of HPC in Norway, which obviously would be colored by my background. And I'll also give some examples of novel use of HPC, which has been enabled through the Competence Center for HPC. So Sigma2 is a publicly owned private company. It's financed by the Ministry of Higher Education and the 4 oldest university in Norway through the Research Council. We provide access to high-performance computing and larger storage resources for research, but also provide access to industry and public administration. Anders said it well this morning that capacity is not really much without competence to use it. And this is also why we collaborate closely with the same funding universities for operating our infrastructure to ensure that competence about using the infrastructure is close to our users. We also participate for Norway in international projects, such as the EuroHPC, LUMI, and also leading the National Competence Center. We have 3 supercomputers in Norway, where Betsy is the largest one. She has about 172,000 cores, provide 1 mega or consume 1 megawatt of energy, weighs 30 tons. So it's a fairly large machine. Fully water cooled, which means that we can actually use the waste heat to heat the campus where it's located at. In addition to Trondheim, where Betsy is located, we also have a location in Tromsø, where we had another supercomputer. And we also own part of the TSD system in Oslo, which is for sensitive data, medical data. We're also currently building out a new data center in a commercial data center, Lefdal Mine Data Center, in the west coast of Norway. So, how does the pointer work? There you go. Yeah, so basically it's a abandoned mine where they used to break out olivine. Currently they only have utilizing only a single floor of the 6 floors available. There's multiple European entities in the mine. I'm not going to mention them by name, but some of them are within automotive industry. We are going to be located at the middle of the mine, having 3 of these streets close to the avenue. You can see some oops, that's not, there you go. Yeah, so you can see some illustrations here about the size, trailer, Boeing 747 and the Statue of Liberty. So it's a fairly large compound. It's close to where the electricity is produced, hydroelectricity. So they have tons of electricity nearby. It's also close to a fjord, where the cooling is fresh from 100 meters deep into the fjord, same temperature all the year around. And when we acquired it, it was a requirement from us that they also had to reuse the waste heat. So they are starting a project now to feed the waste heat into a fish farm for producing salmon to ensure that it's entirely sustainable. We're going to have 3 different buildings in the data center. So the one to the left is the data hall, where all the new supercomputers will be, a staging area where whenever you're arriving, are receiving a large installation that has to be unpacked and rolled into the clean area. And we also currently are installing our storage system in 40-foot containers on the right side, which will be in production by December. The initial size would be about 30 petabyte, but it can grow organically to 70 if required. And our policies for industrial use is that obviously we are bound by the regulations from EU, maximum 20%, but we also have additional limitations by our board to not exceed 5% of our total capacity in sold to commercial industrial use. But the thing is that industrial projects that are funded by the Norwegian Research Council or Europe can be provided access to the same rate as regular research, which also means that they wouldn't consume of the 5%, which is also one of the reasons why we are not close to the limit yet. For commercial access, we obviously have to charge a comparable market price. We would typically look at the hyperscalers to figure out what kind of price they would charge their customers to ensure that we don't ruin the market. We are also leading the National Competence Center for HPC, similar to the Swedish one. We're doing that in collaboration with the independent research institutes SINTEF and NORS. And the reason for doing that is because they have a vast experience working with industry. They have a lot of domain competence within a lot of different scientific domains, and it's a good contribution to our competence center. So there are already a lot of industrial use of HPC in Norway. One of the fields on the left side is between oil and gas exploration. So one is obviously seismic, which many would be familiar with. I figured I'd talk about CSEM, which might be more a mystery to most. So basically, they're deploying magnetic sensors on the seabed, maybe 1 kilometer apart on a large grid, and then towing a large electromagnetic source over the seabed with a magnetic field penetrating up to 4 kilometers into the seabed. And since hydrocarbons and salt are resistive to electromagnetic fields, it would be disturbed by these deposits and then picked up by the sensor on the seabed. After the towing session is completed, they will then release the sensors on the seabed, collect them, extract the data, and then integrate the data into a large data set. And because of this data set is extremely huge, it also requires them to use HPC, which is also actually why they have their own HPC system privately. As typically the modeling would require 2 to 3 terabytes of memory for each of the sets. Another example is between semiconductor engineering. There's a lot of fabless semiconductor companies in Norway. They're producing these microchips, which might be as small as 1 by 1 millimeter, but might have as many as 1 million components. And doing that physically is obviously not feasible. So they're doing all of the development on computers with CAD, or computer-assisted design. And when the product has been fully developed and going into production, they typically create these lithography plates in glass, a set for each of the layers, which is very costly and time-consuming. And to avoid any additional cost and a lot of delay, they have to do a lot of functional testing during the development, which is where they are using HPC. It's strictly not required for the individual tests, but to ensure that they have sufficient test capacity, HPC is very beneficial to ensure that they actually can compete with competitors and reach the market in time. One of the new use cases for HPC is with a company called Kvam. So they already had a mature deep neural network model for automatically detecting field boundaries and seeded acres based on Sentinel-2 GPS photos or imagery. And they recently received a large EU grant for expanding their market throughout Europe, Asia, Africa, and US. And then obviously needed more capacity to analyze all of these satellite images. One of the challenges they had was that they had created a workflow, a large monolithic workflow that we're using in the cloud. It required a huge, costly VM to satisfy all the different requirements that was required throughout the workflow. And when it came to us, it was fairly obvious that it wasn't running really efficiently on HPC either. So we're working with them to help them to split the workflow up in different parts so that the different parts of the workflow could be submitted to the appropriate hardware. So for example, at the GPU dependent task was only reserving the GPU resources for the required time in the workflow, not for the entire workflow. So this is both a cost saver, but also allows for further parallelization when you can then start to parallelize each of these tasks. Another use case is with a company called Cebus. So they are developing an autonomous ferry, which is going to be used for public transportation on unused waterways in cities. One of the issue when you want to, well, actually, they have actually been having a model for running for quite some time in the fjord of Trondheim. But when you want to have a large vessel transporting persons on the water alongside other vessels, there's obviously a lot of requirements for testing. And creating all of these test scenarios on the sea is not feasible. So they have been building a digital twin where all of the different sensors on the vessel are represented, like the cameras, LiDAR, radar, and all of the different control systems for the rudders, thrusters, and so forth, and also all of the AI systems on board. So all the systems that make the decisions about how the ferry should navigate and how it should operate are represented in the digital twin. And they also created a testing environment for a digital twin where they can create the three-dimensional scenarios using a gaming engine so that they could, for example, set up a scenario where the ferry was on collision course with a person in a canoe. They could then test whether the person was detected if he has a red life coat or a blue life coat. Is he still a person if he has a hat? What happened if the ferry is trying to avoid the person in the canoe but then sail into a flock of seagulls? Would it then rather choose to run over that person because it's just one person rather than 10 seagulls? All of those different scenarios have to be tested. And they reckon that they would be needing to test about 100,000 different scenarios for each time they're updating their code or updating the algorithms. And currently they're able to test in real time, meaning that a 4-minute trip will take 4 minutes to test, which means that if you need to test 100,000 scenarios, it's 9 months of testing every time you're updating your model. And this is where the competence center comes in, where we'll help them to create a connection to HPC from the testing system so that they can rather test everything in parallel on HPC, according to how much resources are available, of course. But of course, the best case scenario would then be to reduce testing time from 9 months to maybe 4 minutes, which is something I would like. An interesting fact, the first commercial installation will actually be here in Stockholm. It will be actually by a supervised installation, so there will be a person on board to take over control because they won't have the testing capacity done by next year when it's going to be installed. Another use case we have completed recently and also published a paper on is a project we did with a fiberglass producer. So they were creating these tiny fiber threads that are being evolved into mats and used for constructing a lot of different constructions like a boat hull. But one of the issues when working with glass is that it's a fragile material, so it will break fairly often or have fractures. And we were working with them to see if we could use machine learning to detect if we could see patterns in the current drawn from the electromotors before the glass is actually breaking. And we're able to find an algorithm that could detect the upcoming glass breakage by 98.5%. And this is a proof of concept, so now they are implementing this in production to reduce their waste and production stops. Another interesting project that we are hoping that will be finished fairly soon is with a company called Ocean Term. They have technology for submersing tubes into the water. It's a lot of tiny holes where they blow air into the tubes, and the air would then escape from the tubes to those tiny holes, creating a curtain of bubbles. And with this buoyancy, it will then also bring water from that depth up to the surface. It's been used in Norway to melt ice in the fjords during wintertime to bring warmer water from the depth up to the surface. But now they want to try to use it in the Gulf of Mexico to reduce the surface temperature by bringing colder water up, reducing the energy that would be feeding hurricanes during the hurricane season. So they want to then test what happens if you then deploy this in front of the hurricane coming in, reducing the surface temperature, seeing if it can actually reduce the energy in a hurricane rather than feeding it. But before they are allowed to do that physically in the Gulf of Mexico, they have to prove for the government in the US that they actually won't hurt the climate, the aquaculture, or anything else. So they're helping them to model the behavior of the system on HPC to prove that it will be safe to operate. And then, of course, if the physical sea trials are successful, there would be a new interesting use case in figuring out how to automate the whole process of figuring out where it should be deployed in front of the hurricanes to give sufficient effect and those kind of things. So those was the use cases that I had prepared. We also have some interesting cases that we are starting now. One is in aquaculture. We were trying to use sonar data to calculate the biomass in the sea. So the government can use that for providing licenses and quotas for fishing in a sustained way. We have also some upcoming projects that I won't go into detail, but it's with the Norwegian Customs, which we're looking forward to. I think those are going to be very interesting. But that would be for the next opportunity. Thank you.
Thank you, Roger.